Hello, everyone. So welcome back from the break. We are having our workshops right now. This room is Xanadu's Penny Lane workshop, and we have David from Penny Lane to talk about Penny Lane. So David has various pieces of paper testifying to a life spent avoiding real work, including a PhD in string theory from UBC and a master's in science in particle physics from the University of Melbourne. He recently joined Xanadu as a quantum computing educator, where he hopes this trend will continue. So without further ado, please take it away.
Thank you. Okay, so for those who have just arrived before the previous announcement, if you want to navigate to cloud.xanadu.ai and create a cloud account with Xanadu, then you'll be able to follow along when we get to the workshop part of the talk. So just let me know if you have trouble at any point, but hopefully everyone should be able to get some version of Penny Lane working on their computer so that you can actually do the workshop. Okay. So the title of my talk is From Pancakes to Perfect Privacy with Penny Lane. And I'm going to give a sort of broad brush overview of quantum computing, which is naturally biased and designed to kind of lead as a matter of kind of inevitability to Penny Lane as a great product. And we're going to be looking at an application to perfect privacy. All right. Oh. Okay, so the first part is going to be the quantum pancake stack. We're then going to actually do the workshop, and we're going to end with some kind of tips for learning more. So the quantum pancake stack. Quantum computing, as I'm sure you've sort of learned by now, is a really interesting but really hard problem. Oh, and if you've just arrived, for the gentleman who just arrived, maybe chat to your neighbor about how to get Penny Lane installed if you don't already have it installed. I'll just go back to stuff. Just check out cloud.xanadu.ai and create a free account. Okay, same for the gentleman on the left there who just arrived. Okay. Okay. So if we want to get a quantum computer which works and does cool things, we need to stack a bunch of things on top of each other. Okay. Each of these things is a difficult problem. It's something big, it's juicy, you can sink your teeth into it, you can spend a whole career on it. So I argue it's a little bit like a large stack of pancakes. And what we're going to do is zoom in on each pancake and chat about. So the pancake right at the bottom of this stack, which we build everything else from, is the qubits. Okay, you've talked a lot about qubits, I'm sure. And the idea is that we need to encode zeros and ones. So the 0 state and the 1 state in some robust way physically. This is a really difficult experimental problem. It's a difficult technological problem. We need to satisfy a bunch of criteria. And there are a lot of smart experimentalists and technologists working on this. Okay, I'm going to talk about some of the approaches later. The next layer up, once we have qubits, is to connect them into circuits. And hopefully you've talked a bit about circuits. You've talked about error correction. I saw some error correction stuff here as well. That's another aspect. So we want to run computations. We are going to manipulate some qubits. But as we run computations, we are going to accumulate errors. And in the long run, what we'd really like to be able to do is, fix those errors as we go. So this picture that I've drawn here is meant to be, instead of a computational atom, which was the single qubit, this is a sort of computational molecule. Okay, so it's a qubit with some other things attached to it to correct errors as the qubit sort of goes through the circuit. So again, architecture is a really, really difficult problem. Perhaps it is the most difficult problem. Okay, programming. So now we can run circuits in my imaginary pancake stack. We actually want to be able to tell the computer to do stuff. Okay, so this is the realm of software. So you want to have some way of interfacing with a computer and saying, hey, please, break RSA for me or whatever it is. And then on the other side, what the computer can do and how to do it in a smart way rather than kind of an inefficient way is the realm of algorithms. So these two things, I think, tend to go hand in hand. They're both at an abstract level. Hey there. Hey guys. You may want to, when you sit down, if you want to just like chat to a neighbor and try and get access to Penny Lane, just so we can save time later, but we'll go through it later as well. Okay. So I'm going to bundle these two things together into what I call a programming layer. Okay, so you have software and you have algorithms. Okay, so we have a programmable quantum computer in this hypothetical scenario. Are we done yet? The answer is no, because there's no reason to think that we should actually care. Okay, what we want to be able to do is apply our quantum computer to solve useful problems, and not just useful problems, but to do it faster than a classical computer can do it. Okay, otherwise there's no reason to care about quantum computing. Okay, so let's just focus on the second part first. So, can we find something that a quantum computer can do faster as opposed to something that is useful and faster? So the challenge of, faster is what's called quantum advantage. Okay, so for instance, can I do something on a quantum computer in, 10 or so microseconds that would take a powerful classical computer 9,000 years? Okay, it turns out that the answer is yes. There's a bunch of different machines that exhibit quantum advantage. Are the tasks useful? Well, it depends how much you care about, like, I don't know, Gaussian boson sampling, things like that. I would say that in general, the answer is no. And we haven't yet arrived at really, really useful applications that can be done faster on a quantum computer than a classical computer. So this is sort of the frontier. Okay, and when I say, okay, the next challenge is, can we do useful tasks faster? And can we do that now or in the near future? What I mean is without error correction. Because like I said earlier, error correction is kind of the bottleneck. It's really, really hard. Okay, and the last layer, this is Penny Lane. Penny Lane, you're in the right place. All right, the last layer is access. So once we have a quantum computer that can do useful stuff, there's a question of, how do we make quantum computation and quantum computers available to the world at large? Do we make it available to the world at large? So, there's two different models. Well, there's many different models. There's a spectrum of models. But on one extreme end of the spectrum is lock the quantum computer in a lab, okay? Form some sort of medieval guild of esoteric technicians who jealously guard the secrets of the quantum computer and charge people exorbitant fees to use it. Okay, that's one way of doing things. That's the way that things have often been done in the past. Model 2, on the other end of the spectrum, is basically the sort of open version. So instead of locking their quantum computer in a lab, put it on the cloud, make it available to anyone who has an internet connection. Another element of access is to explain how it works, make it really clear, open source all of your software, and so forth. All right, so you can kind of guess where I'm going with this. But here's a quick summary, quick recap of the layers. At the bottom, we have qubits. That's the zeros and ones. They're the sort of computational atoms. Next layer up is architecture. So that's combining our qubits into circuits, applying gates, initializing them, and potentially doing quantum error correction, though that's kind of like a medium to long-term goal. We have programming. So that's software and algorithms. So how do I tell the computer to do stuff, and how do I do it in a smart way? We've got applications. So can I find stuff that is useful and can be done faster on a quantum computer than a classical computer? And finally, access. How do I make it available to the world? Okay, awesome. So the punchline, the whole pancake analogy is really just leading to this. Xanadu is what's called a full stack developer. That's a technical term. The stack here doesn't actually refer to pancakes, but in my analogy, it does. We work on all of the pancakes. We're trying to cook them. We're trying to put them on top of each other, whatever, I don't know. The point is, each of these layers is something that the company works on. So we have a qubit layer. Our qubits are made of light. This has a bunch of advantages. You can ask me about that later if you want. We have people who work on architecture. So we do integrated chip design. We have a lot of people doing hard optics stuff. And we have an active R&D group working on quantum error correction. On the programming side, and this is what I work on, we have various domain-specific quantum programming languages. So Penny Lane is the sort of all-purpose one. It's often kind of billed as being for quantum machine learning, but that's just one of the things it can do. We also have Strawberry Fields, which is for photonic quantum computing and continuous variable quantum computing in general. I don't know if you've talked about that, but feel free to ask me about that later. Not everything is named after a Beatles song, but most things are, in case you're wondering. In terms of applications, we have a machine called Borealis, which recently achieved quantum advantage, and what I think is really cool, a really cool step, deployed it to the cloud for the first time. So, people at home could kind of verify, something in 30 microseconds that would indeed take a classical computer 9,000 years. And we have, again, a large R&D group working on various applications. So quantum machine learning is one of them. And I know that sounds like the buzzword of the century or the buzz sandwich of the century. I don't know. But it is a real thing. And it's actually very interesting. So that's one thing that we look at. Another big thing is quantum chemistry, okay, which is sort of somewhat less exciting, but perhaps more useful. And finally, the access layer. The company is built around a philosophy of making everything open source. So our code base is open source. You can contribute to it. You can kind of like create issues. You can do a pull request, whatever. Please contribute if you're interested. Our various machines are available on the cloud. And if you haven't signed up already, please do go to cloud.xanadu.ai. We'll kind of go into this in a second, but and we have a lot of educational content designed to make it totally intelligible to anyone, maybe anyone with a kind of, an undergraduate background in linear algebra or something like that. But the idea is that we want to make it as accessible as possible. So that's the philosophy of Xanadu. And I can kind of encapsulate it in a mission statement to build quantum computers that are useful and available to people everywhere. And I understand availability is not just being about having an internet connection and I can run something on Borealis from like, Antarctica, which is cool. But also I can understand what I'm doing. Okay, the resources are out there and they're made available to me and I can, figure out what it means to run that thing on Borealis. Okay, cool. So at this point, I'll just pause and ask if there are any questions. I'll have some time for questions at the end as well, but if there's anything pressing now, please feel free to interrupt me. Okay, did you have a question? Yeah. That's right, yes. Yeah. Yeah, okay, so I should have prepared a slide on that actually. Yeah, so the coding camp is coming up very, very soon. If you go to the Twitter, so the Penny Lane Twitter, I'll have a link to that at the end. You can find a link to the code camp site on Twitter. And you can click it, you can register, and you can get started. It's actually starting very, very soon. So yeah, so I'll talk about that at the end, but thank you for bringing that up. Appreciate it. It's like I had a plan, it's like, okay, good. So we're now going to talk about perfect privacy. So if you haven't already, please navigate to Xanadu Cloud. So what you need to do first of all is go to cloud.xanadu.ai and create an account if you haven't. Okay, so I mean, I'm going to have trouble because I don't have internet. But is anyone having issues creating an account? Yeah. Oh, okay, that's a great question. Yeah. So I'd suggest if anyone does not have Wi-Fi access, and I'm having issues with reception in here as well, maybe sit next to, well, I don't know if we have physical distancing that we need to worry about, but otherwise maybe sit next to somebody who does have access, and that way you can follow along. Does that sound good? Okay, cool. Okay, awesome. All right, so once you've signed up, you should be able to see this landing page. And once you're here, just click on Notebooks. Okay, and that should open up a little kind of Jupyter Lab, okay, dismiss. A little kind of Jupyter Lab widget, and you can just create a new notebook by pressing the plus button at the top left. Okay. And it'll come up with this little launcher page, and you can just click at the top for a Penny Lane notebook. So if you can do that, and let me know if you run any issues. Yeah. Yep. No, you don't need to. I mean, part of the reason I'm saying you should go to the cloud anyway is for advertising purposes. But you can install it locally. Please do. Yeah. Okay. Cool. All right, so I'll give you just another 30 seconds. Raise a hand if you have any issues or just shout out. Okay. So at this point, oh, all right, good. At this point, what we're going to do is we're going to go into a little coding example. If you don't have any experience with Python, that's okay. You can just follow along. I'm going to make the notebook available later somehow, hopefully. You certainly don't need any experience with quantum programming. And You don't need to write any of this writing down. This is just for you to read later and to remind myself what to say. But I do want you to follow along with the coding examples. And if something doesn't make sense or it's not running, just let me know. So the first thing we're going to do is to actually import Penny Lane. So it lives inside Python, and we need to kind of tell Python to access the library and all of the stuff inside it. So we say import Penny Lane, and then we're going to give it a name because I'm too lazy to write Penny Lane as QML. Okay. So QML stands for quantum machine learning. This is part of the billing that we're trying to change a little bit, but QML is 3 letters, and that's short. The other thing we're going to do is import a numerical package, which is useful, called NumPy. So from Penny Lane, import NumPy, and again, because I'm lazy, I'm going to say it as NP. Okay, so that's the first thing to do. And this is, in some sense, living in the programming layer. It's about how to interface with a quantum computer, or things which are pretending to be quantum computers, as we'll see shortly. All right. And since this is the workshop section, please just let me know if something is unclear. Just please feel free to ask. All right. And can people see this? Do I need to make it bigger? Maybe I'll make it a bit bigger. Okay. All right. So the next bit is the qubit layer. So we actually need to tell Penny Lane which implementation we're using. So what is going to physically realize our qubit? Okay. So we can think about this, that this is in Penny Lane called a device. And we can think of it as kind of like a bubble wrapping the qubit. So the qubit is kind of like, it's a concept, it's a logical concept, it's an idea, it's a state of mind, whatever. And then we need to make that physical. And the device is the thing which tells us how to make it physical. All right. The default option in Penny Lane is actually not physical, it's a simulator, or rather it is physical. It's just getting your very physical classical computer to pretend to be quantum. Okay. And we're going to do that because as cool as it would be to use Borealis or something like that right now, Borealis has a day of rest on Saturday, which is unfortunate. I wanted to do something with it, but it's sleeping. Okay, so what we're going to do is we're going to define the device that will implement, let's just say a single qubit. So device, I'll just call this device dev. We're going to refer to it later, is qml.device defaults.qubit. And then we're going to give it a couple of other parameters. So we're going to say wires equals 1. That means we just have a single qubit because we're imagining this as a wire, an input into a quantum circuit. And then shots equals 1. And that one I'll explain later, but it basically means that when we do measurements, we're literally just going to measure once and see what happens. Okay. And kind of like a quick point, classical computers are not good at simulating quantum computers. They suck. So as the number of qubits increases, the cost to simulate classically grows exponentially. So you really want to have access to real hardware. And I'm not going to kind of go through it now, but Penny Lane has access to many real devices as well as the fake devices, and even better simulators than the default simulator and so on. And you can explore that. Again, like I say, I'll make this notebook available, and there's a bunch of links in it and stuff like that, and you can see what other devices you can use. Okay, so the next step is to combine the qubits into circuits. And in Penny Lane, we can just think of circuits as this sort of objects floating in space. There's gates, they act on wires, but those wires are not yet connected up to qubits, okay? So we're separating those 2 bits out. And the nice thing about that is that we can implement this as just a regular function. There's nothing quantum about it. It's just a function. It's specified by some sequence of gates. It's like a graph or something like that, okay? So we're going to do an example. And my understanding is that you talked about quantum cryptography yesterday or earlier today. Is that right? Okay, awesome. All right, so hopefully this is going to seem not totally wild and unfamiliar. But we're going to implement some very simple circuits. And I have some gray lines here. And these are meant to indicate classical bits. Okay, so B is a classical bit. I is a classical bit. They can either be a 0 or a 1, and that's the only possibilities. No combinations allowed. And they're going to be controlling some other gates. Okay, so this is just the same as usual, like when you have controlled NOT gates and a controlled whatever gate. It's just that the input bits are classical. If it's 1, you apply it. If it's 0, you don't. So let's implement these. So I'm going to call the little circuit on the left Alice prep. The inputs are B and I. And let's say if I is equal to 1. So with Python, if you want to check if something is equal, you need to use a double equals sign. So a regular equals sign is a variable assignment. Okay, and then what we're going to do is say if that control bit is equal to 1, then let's apply the gate x. And in Penny Lane, we write QML, so that's the shortcut I'm using for the name of the library, Pauli x, and then the y that it acts on. In this case, we'll just call it 0. Okay, I could have called it like 16 or something like that, but because I only have, in my device, I'm only going to have 1 qubit, and they're indexed computer science style, starting with 0. That's why I'm using 0 here. Okay, and then I do the same thing with b equals 1, then I apply the Hadamard gate. So hopefully you've seen that a bunch now. And I just do the same thing. Okay, so that's the first one. And just a quick recap, x is just like a NOT gate. And h takes us from the computational basis, 0 and 1, to a sort of plus minus basis. Okay, it's sort of rotated. So hopefully what I've just said doesn't sound like gobbledygook. Are people cool with this? Like if I just say, okay, some thumbs, good. All right. So, all right, then we're going to define this very similar circuit called Bob check. It's very, very similar. In fact, I'll just copy and paste my code. Okay, so this does the same thing. It's got a third control bit, B prime. And if that is equal to 1, then it's going to apply a Hadamard gate. So this may seem like a totally random example. And before we explain what it actually does, I'm going to explain how we can implement this like seemingly arbitrary circuit or arbitrary pair of circuits. So the basic idea in Penny Lane is that you have these two things. You've got devices which are implementing our qubits, and then you have these circuits which are sort of these freely floating platonic objects, and we want to kind of tether them together, okay, and then execute the circuit using these physically implemented qubits. Okay, so we can attach a device to a circuit using what's called a Q node. You can think of this as the sort of line in between. So the syntax for doing this in Penny Lane is just at QML QNode, sorry, at QML.QNode, then the name of the device that we're going to attach our circuit to at dev. And what I want to do in my circuit now is I'm going to run those two circuits that I defined above. So Alice prep and Bob check. And then I'm going to get Bob to do a measurement, or I'm just going to do a measurement, but I'm imagining that Bob is doing the measurement. Okay, so define, and I'm going to call this BB84. And hopefully, did you talk about BB84? Okay, good. All right. So this is a circuit for doing BB84. Okay, so I've got my 3 bits, B, I, and B prime. First I do Alice prep, B, I. Then I do, whoops, that's not what I meant to do. Then I do Bob check, B prime. And then the Q node needs to end with a measurement. It needs to spit out a number. The reason it's actually called a Q node, first of all, that stands for quantum node. And what I would like to think of this as is, I imagine like a big graph, a computational graph, where each node on my graph is like a number or something that I can chain together with classical logic. But quantum things can be going on inside those quantum nodes. All right. But what I need to make sure is that it terminates in some number that I can write down on a piece of paper, not some kind of weird superposition of pieces of paper or anything like that. It's got to be real. So we have to terminate with a measurement. Let's say return. And then what I'm going to do is I'm just going to get it to sample once. Okay, and this is where the shots equals 1 came in earlier. So that said, if you're going to sample from this circuit or sample from this device, just do it once. Okay, and that's what's going to happen when, say, Bob measures a qubit. Okay, so QML sample, and then we're going to do the usual thing of just measuring in the computational basis. And another way of doing that is just measuring the Z, the Pauli Z. So we'll say, okay, measure Pauli Z acting on the 0th wire, which is the only wire. Okay, cool, and that's it. All right. Okay, so I said some stuff already. Blah, blah, blah. This is the circuit that we have, although in a sense, the stuff on the left of the first Hadamard is to do with Alice. Okay, so she's preparing some qubit, and the stuff on the right, including the measurement, is Bob's. Okay, and this may look boring, but this is an implementation of the BB84 protocol. Okay, so it sounds like you've talked about that already, but I'll just talk about it a little bit because it's very cool. So the reason this is interesting is because it means that Alice and Bob can share secrets in a provably unbreakable way. Okay, and maybe that requires a little asterisk. So the first thing to say is if Alice and Bob wanted to share secrets in a provably unbreakable way, say Alice wants to hand Bob a secret bit that no one could ever break. The easiest thing for them to do is to meet up, flip a coin, go away. Okay, now they have a random bit that they can use. And the thing that they do is like Alice says, okay, I want to send you this particular bit. I'm telling you which horse to bet on out of 2 horses. And I'm going to just flip the bit if the outcome of the random coin flip was heads. And if it's tails, I don't. Okay. And in fact, if Alice wants to send an n-bit message, then they just need to flip a coin randomly n times, and then they have something which is provably unbreakable because anyone else who intercepts it will just see a string of n random bits. Okay, even though secretly Alice's message, all of the n horses to bet on or whatever it is hidden inside. So this is really cool. The problem is that they need to get together beforehand and flip a bunch of coins. And it would be really nice if they could flip coins remotely and somehow communicate that to each other. So that's the whole point of the BB84 protocol, is so that they can do what's called quantum key distribution. So I hope that, I assume that you talked about all of that. So cool. Okay. So the basic idea is that I here is the secret bit, okay, that they want to share. B is a choice of basis. So, if B is equal to 0, then you're in the computational basis, 0 and 1. If B is equal to 1, then you apply a Hadamard, and that takes you to the plus minus basis. Okay, so you just kind of, you go from this to this. Okay, and the cool thing about the plus minus states is that when you make an observation, they look like random coins as well. Okay, so you just get heads 50% of the time and tails 50% of the time. Now, Bob is also going to toss a coin. The outcome is B prime. So we're imagining all of these bits as random. And if he gets 1, then he's going to apply a Hadamard. In other words, he's going to measure in the plus minus basis. That's equivalent. So like if I have this is a Z measurement here, but if I apply the Hadamard, I'm going to measure in that basis because h squared equals the identity. Does that make sense to people? Okay, good. I assume that you went through this, but I don't want to rush. Okay, so the outcome is the following. If Alice and Bob happen to prepare and measure in the same basis, so B equals B prime, then Bob's measurement immediately tells him what the secret bit I is. Okay, that's really cool. And if they're different, then Bob is going to get a random outcome, and they have to discard it. Okay, and how does he know to discard it? Alice can actually just say publicly what B is, and this is the thing that's really cool about it. So she never says what I is. She can just say what B is, and then Bob can say, oh, hey, you know what, my B prime is the same. So good, I can use this bit, I can keep it. So we can just do a little example using the function that we made. So let's go B, I, and B prime. And this is why I imported NumPy all those years ago. Random, randint. We put a 2 in here to say we want to select between 0 and 1. And then we'll say size equals 3 because we want 3 random numbers. And then let's print something. We'll print Bob measures, and then BB84, BI, B prime. Full stop. And then can he keep this bit? And then we'll, okay. Okay, so here's a random example. Bob measures -1. Can he keep the bit? The answer is true. So their bases agree. We don't even need to look at what the random numbers are. We've summarized all the important information. The secret bit is encoded into the -1 according to the usual convention that somewhat confusingly corresponds to I equals 1. That's fine, we'll ignore that. And Bob can keep the bit because his basis agrees with Alice's. Okay, so how are we going for time? We've got another 10 minutes, is that right? I think it's 4 o'clock. I mean, 5. The other, yeah, okay. Okay, so would it be possible for me to send this, to make it available to people as well? The notebook? Right now. No, later, like, okay, cool. All right, so maybe, so I have a little challenge. Due to various organizational issues, I was meant to arrive like bearing swag, Xanadu swag that you could take away. I don't have that. And I also don't have a huge amount of time. So I realized I could kind of kill two birds with one stone and make a little challenge question available. This may be like super easy because you've already discussed this, I don't know. But if you wanna come up with some solutions, send them to me. And then if yours is the first correct solution for a given question, then we'll figure out some way to get you swag. But anyway, here are the challenges. So what I've described so far is in some sense it's kind of ridiculous, because what's to stop an eavesdropper from simply intercepting Alice's qubit, making the measurement herself, and then sending it to Bob? Okay, what's wrong with this strategy? So in fact, there's an even better strategy, because you might say, oh, well, a measurement is going to affect the outcome, right? So like a measurement is destructive potentially, and maybe they'll be able to detect it. We'll come back to that later. First thing, suppose Eve has a quantum Xerox machine, and she can just copy any state. How could she determine the state that Alice sends and learn the secret bit I without alerting either Alice or Bob? Does anyone want to volunteer? And if you've already covered this, that's cheating. No. Did you already cover this in your quantum cryptography thing? Okay, great. All right. So, all right. Eve has a quantum Xerox machine. I give her a state. She copies it. Yes. It is, but that's cheating. Just ignore that. Yeah. Exactly. Yes, that's right. She's got to copy it multiple times, but when she's copied it, she can copy it as many times as she wants, because she can copy this one, and then she can copy that, and then she can copy that. So let's say she's got 100 copies. What does she do now? Yeah. Okay. Yep. Yep. That's exactly right. So this is okay, but we can be more specific. Yeah. Yeah. Okay, so I'm going to say this is the correct answer. If you want swag, what I will ask you to do is send me a precise protocol for figuring out what the state is. Okay, and then that will net you the swag. But that's exactly the right idea. Okay, but there are no quantum Xerox machines. Okay, so this is a crucial result in quantum mechanics called the no cloning theorem, and it basically states that you cannot copy an unknown quantum state. You can copy quantum states, like, somebody gives you a 0 and you're like, well, I can make as many zeros as I like using, I don't know, photons or electrons or whatever it is. But an unknown quantum state cannot be copied. So Eve has to measure the state that Alice sends if she wants to learn anything about it. Okay, it turns out that's not totally true. You can imperfectly copy things, and that's kind of advanced and interesting and fun. But let's just assume that Eve has to measure it. Okay, what is the probability that she does this non-destructively? In other words, without affecting the state? Yes. Bam. Okay, and why is that? Yeah. Yeah. Bam. Okay. All right. Come to me afterwards, and we'll figure out the swag thing. Okay. Okay. Good. That's a perfect answer. So did everyone understand that? Okay. So Eve has to measure in the same basis that Alice prepares it. Okay. And then she knows what it is. And there's a 50% chance of that. It's a coin flip. Okay. Well, the coin flips have to agree, and there are 2 out of 4 ways of that happening. So okay. Good. If Eve measures in the wrong basis, she changes the state. Is everyone cool with that? Okay. So okay. Good. How could Alice and Bob potentially detect that this has happened? Okay, yeah. And with what probability can they do this? Yes. Yes. Exactly. Good. Yeah, yeah. Good. Okay, perfect. All right, you also come at the end. And actually, I'm going to be nice. So for the people who have answered questions, just please. Okay. Good. And maybe because I want to leave. Okay. So there's some math. Yes. Yes, I mean, it's conditional. There's a 0.5 in front, yeah. Okay, so I'm gonna end with two more interesting questions. So first, it seems like the odds are tilted in Eve's favor, okay? Because if you add these numbers up, you get 0.75. So it seems like she's got a really good chance of actually eavesdropping successfully. So, and I'm not gonna actually ask for any, well, unless people wanna guess, but okay, assuming that Eve intercepts, measures, and sends every qubit off to Bob, explain how Alice and Bob can make the chances of detecting interference arbitrarily good, so arbitrarily close to 1. Yes. Yep. Yep. Okay, so this is pretty much right. And I'm going to say the same thing. Write this up as a formal protocol and analyze the numbers and double check that you can get it to above 1 minus epsilon for any epsilon. And then that will be another bit of swag. Okay, and then the last thing is write a penny lane implementation of the foregoing and confirm all of the numerical answers to the previous thing. Obviously, we're not going to do that now, but if you write that up and send it to me, I will organize some kind of very, very cool swag. I promise. So I'm sorry I didn't bring anything. So, that's the end of the workshop section. We've got like 3 minutes left or something. So are there any questions about, penny lane or, I don't know, swag or whatever it is that we've been talking about? Okay, so I'm going to, if you do have questions about penny lane, let's actually continue. Let's just go to the last section, which is learning more. So this is going to be a quick and extremely biased review of resources that exist out there for learning more about quantum computing. And also penny lane, that's not going to be so biased. So the first thing I want to point to is something called the Xanadu Quantum Codebook. So this is codebook.xanadu.ai, and there's, I don't know, a PR code if you like those. I mean, a QR code, not a pull request code. This is a free online and interactive textbook. It teaches both quantum computing, but it teaches it via penny lane. This is kind of like, it's not exactly my baby, but I was like one of the co-parents of this thing. So I was a resident and I helped create this. So, I think it's really cool, but I am extremely biased. But just quickly, it's built on a code first philosophy. So the idea is you want to actually learn how to tell the computer to do stuff while you're learning about quantum computing. So that's the idea. It's also built around principles of adult learning. So it doesn't treat you like a baby. It says, okay, here's why you should care about this. Here are some applications and so on. Okay, we also have a YouTube channel. So we've got a bunch of tutorials. They cover basic usage. So for instance, how to create a cloud account if you didn't get to do that while you're in the room, that you can learn about it there. How to run jobs on Borealis, as well as more advanced topics. So, an introduction to BQ. I know you guys just did this, but if you wanted to learn about it and see how it's implemented in penny lane, you could go watch the video. And then the last thing is penny lane demos. So we have a bunch of demos. This address is a bit of a mouthful, but the basic idea is that these are kind of like long blog posts which have a bunch of code in them. We've got blog posts as well, but the demos will walk through things in a careful way, like tutorials. There's core concepts, but there's also advanced stuff. So for instance, I've written one where we just sort of implemented a paper that came out that we thought was cool. So there's a bunch of applications to quantum machine learning, optimization, quantum chemistry, and so on. So this is sort of like, research frontier stuff as well as basic usage. And a cool thing about this is that if you really like demos, you can contribute your own. So this is the community section at the bottom right. And yeah, finally, I'll end with like a little, social media kind of roundup. We're very active on GitHub. Everything is open source. So if you want to make an issue, a pull request, to contribute, please get involved. We have a forum for discussing penny lane. So it's discuss.pennylane.ai. So you can go and, kvetch about our syntax or whatever. That's welcome. There's a Slack channel, so xanadu-quantum.slack.com. It's pretty active. If you have questions about the language or just stuff generally, please feel free to get on there. And finally, we're reasonably active on Twitter, so please tweet. And yeah, so there is a code camp coming up. It's called the Penny Lane Code Camp. So if you want to get involved, solve some problems, win some prizes, have fun. That's coming up very soon, and the details are on the Penny Lane website. So yeah, that's pennylane.ai, and then you can find details on the Twitter as well. that was pretty much it. So thank you. Okay, I don't think I left any time for questions. So.
He has a couple of quick questions. The other room is running a bit late, so we do have a bit of a time.
No, perfect.
So, like you said, Borealis achieved quantum supremacy. What proof actually, I mean, what sort of argumentation goes into proving to other people that that actually happened?
Okay, yeah, that's a good question. So part of it is like you run a job and you can say, okay, this job completed in 30 microseconds or whatever. And here's the output from the job. Here's a log and stuff like that. So people believe that the computation actually happened on Borealis. So the harder thing is showing that there's no way of doing it quicker on a classical computer. Now, this is actually kind of like a very subtle issue. If I tell you, oh, there's no way of doing it quicker, that means that in some sense, I have to go away and survey every possible algorithm. Okay, it turns out that in general, that's just, we don't know how to do that. Okay, so there's this very famous problem, so P equals NP, which is exactly about this. So there are problems that seem to be hard, but we don't know that they're hard. Proving that they're hard involves surveying every possible algorithm. And it turns out that there are lots of things that appear to be hard, and then somebody comes up with a clever way of doing it. So very often when people talk about quantum advantage or quantum supremacy, what they really mean is the best known algorithm. So, and then you can sit down, you can do an analysis where you say, okay, well, the scaling for, this particular, for a simulation of this on a classical computer goes like blah, it goes like, e to the n or whatever. And if you have this many gigaflops, then it's going to take 9,000 years. So that's the way that it works. You assume that you know that, well, you're comparing to the best known classical algorithm. So does that answer the question? Okay, awesome.
Any more questions? Yeah, actually, I have a question. So I know you said that you just joined the Xanadu team, but
yes.
How much would you say that Penny Lane's work or the software aspect of this team's work works together with or works with the hardware side of Xanadu as well?
Yeah, great question. So the Penny Lane is less connected to the hardware, but some of the other languages that we have, so particularly Strawberry Fields, which is for photonic quantum computing. So it's a programming language which is really explicitly designed for using on the computers that we build and computers like them. And so there are people on software who are kind of working on Strawberry Fields. The Penny Lane, so when I was preparing this, I'm like, oh, it'd be cool to like do BB84 like on Borealis, like, we could just like, or like, let's, I don't know, like violate Bell's inequality or something like that. And I sat down and started trying to work out how to map it onto that. And I was like, whoa, this is really hard. It's extremely non-trivial. So yeah, we don't work as much with hardware as people working on the sort of the photonic software side. It would be nice to change that. But there are other hardware type things that we do. So, if we write a paper in quantum machine learning, for instance, we'll go and find a machine where we can implement it, which may not be one of our machines. It may be like IBM or, Microsoft or Google or something like that. Good question.
Yeah, and there was a lot of swag mentioned. We do want to mention that we also have swag from Xanadu. So we gave away Xanadu t-shirts to our first 50 registrants.
Oh, cool. Okay, good.
So there's a lot of Xanadu swag moving around this
Well,
conference.
I remain true to my promise. And for those who I already mentioned, please come and see me afterwards. And the same is true. If anyone does this implementation of BB84 and even stuff like that, please email me. I think that'd be really cool. And I would love to turn it into a demo. So maybe that's kind of a cool thing that we could potentially do. Okay, cool.
Sounds good. Yeah, let's thank David once more.